I wanted to make a video about small turbojet engines, and obviously for radio controlled planes there are some very small ones, but on this channel I tend to stick with aviation engines used for manned applications. For RC planes and to an extent also military drones, different rules apply. For example, reliability does not need to be exceptional, and neither does fuel consumption. The thing is, for manned applications, turbojets don't scale down very well in terms of remaining relatively fuel efficient. The other thing is the turbojet is essentially a dead technology in the manned aircraft sphere. Now, I need to qualify that. I'm not saying there are no manned turbojet aircraft left in the world. There's plenty. I'm saying no manned military aircraft or airliner has been designed around a turbojet engine in decades. I said this in a recent video and a few viewers commented that isn't true. Jet fighters all use turbojets. But they don't. Modern fighter aircraft use turbofans. The last US fighter aircraft powered by a turbojet was the F-4 Phantom II, an aircraft designed in the mid to late 1950s. The last European turbojet fighter was probably the Dassault Breguet Super-Étendard from the 1970s. And the last Soviet turbojet-powered fighters include the MiG-23 and the Su-17 family, both designs from the 1960s. While some of these were produced into the 1980s and even the 1990s, these fighters were all eventually replaced by turbofan-powered aircraft, more specifically low bypass afterburning turbofans. These aren't true turbojets. Unlike turbojets, they do not create all thrust with the engine core. A meaningful portion is also generated by a fan or a set of fans. Just one example is the F111 Aardvark's Pratt & Whitney TF30 turbofans, where clearly some air bypasses the engine core and doesn't get combusted at all. In airliners, the turbojet essentially died out for new designs in the 1950s, with supersonic jets like the Concorde being exceptions from the late 1960s. The main reason turbojets were made obsolete barely 2 decades after it first entered mass production is because turbojets are extremely fuel inefficient, even for military applications. The turbofan offers some real advantages over them, like being quieter, which matters for civilian use, offering better static thrust and thus better takeoff performance, as well as being efficient at lower speeds. I'm digressing a bit, but I wanted to create the necessary context to highlight how exceptionally strange it is to have turbojets on the market for small manned aircraft. PBS Valka Bitesh is a Czech turbine engine manufacturer. They produce the TP100 turboprop and a range of small turbojets, the smallest currently in production being the TJ40G1, which is just 147 mm in diameter and 304 mm long, weighing 3.4 kilograms. That's 7.5 pounds. While most of these small turbojets PBS offers are targeted at powering unmanned aerial vehicles and missiles, there is one variant also targeted at experimental aviation, the TJ100. It has a diameter of 272 mm and is 636 mm long with a weight of only 17.6 kilograms. The engine has a maximum operating speed of Mach 0.9 and a maximum altitude of over 32,000 feet. Specific fuel consumption is 0.118 kg per Newton hour, which translates to around 184 liters per hour. That's clearly not fuel efficient, but note that this is at full thrust at sea level and consumption will come down as power is reduced in cruise. It produces up to 1,250 newtons of thrust at sea level. But how much is that really? Well, the small Williams FJ33, which powers the Cirrus Vision jet, produces 8,200 newton. Keep in mind the FJ33 is a turbofan, not a turbojet. I'm only citing it for reference as it's a relatively well-known small turbine engine. The TJ100 has a TBO of 300 hours for the latest variant. The only references I could find to its cost put it between $65,000 and $86,000, so not exactly cheap. So, how does the TJ100 compare to other small turbojet engines? There is the TEI TJ300, which produces a comparable 1,400 Newton, but unlike the PBS, it is strictly marketed as a missile engine. If our criteria is that a turbojet must be officially targeted at manned experimental jets to be considered here, it leaves almost nothing else on the list. One older engine that does qualify is the microturbo TRS-18, a small French turbojet from the 1970s. It produces a maximum of around 1,100 Newton for takeoff, has similar dimensions to the TJ100, but is about twice as heavy. The lack of small turbojet options is no real mystery. They are very fuel inefficient and are very expensive. Still, I doubt there's a cheaper way to power a plane capable of over 250 knots than a small turbojet. Before we look at applications, let's first look at the design of small turbojets. Turbojets are fairly simple in design, and scaled down they become simpler still. We'll consider the TJ100, but all these small turbojets share a similar basic design. Air enters at the front into the centrifugal compressor, which takes air in axially, then moves compressed air out radially in all directions. That's why it's also called a radial compressor. It only has a single compression stage with a pressure ratio of around 3.5 to 1. Though that's an estimate, as PBS doesn't disclose that information. Because of how compressed air is accelerated radially, the airflow needs to be turned 90 degrees rearward to feed the combustion chamber. Keep in mind this flows rearward right around the engine. The compressed air can flow all the way around to enter the combustion chamber. It first passes through a diffuser, which increases static pressure and lowers air velocity, important to avoid flameouts. The combustion chamber is of annular type, which you can think of as a ring running 360 degrees around the circumference of the turbine section. Fuel is added and the mixture of compressed air and fuel is ignited. The hot expanding gases then flow out through the nozzle guide vanes, which redirect them to meet the turbine blades at the optimum angle. As the hot expanding gas exits through the turbine blades, it spins the turbine, and the gases then flow through the exhaust nozzle, converting pressure into kinetic energy, which creates thrust. The turbine is directly connected to the compressor, so the turbine rotor spins the compressor, which keeps feeding the engine with compressed air to combust. The TJ100 is a single shaft engine, so everything in the engine core that spins does so at the same speed, as they're all connected to the same shaft. Maximum engine RPM is 60,600. And that's it. Extremely simple and quite possibly the production engine for human carrying aircraft with the fewest moving parts. Unfortunately, this low moving parts count does nothing for fuel efficiency. Fuel consumption runs at about 184 liters per hour at full thrust at sea level, a figure derived from the specific fuel consumption stated on the PBS website. But this comes down to a claimed number of 68 liters per hour in cruise at altitude in at least one of its applications. To illustrate how inefficient these engines are, for comparison, here are a few light aircraft piston engines with similar fuel consumption. The 315 horsepower Continental TSIO 550 in the Cirrus SR22T burns around 62 liters per hour in cruise. And Lycoming's 300 horsepower IO 540 in a Cherokee 6 burns around 60 liters per hour. Fuel burn for both examples can vary a bit. These engines don't really compare well with the TJ100 though, as they power significantly larger 4- and 6-seat aircraft, which the TJ100 cannot. A more comparable piston engine would be something like the 80 horsepower Aero V, which uses less than 20 liters per hour. Sure, throttling the turbojet back lowers fuel burn per hour, but this actually worsens specific fuel consumption. This is because turbojets are designed around a specific operating point, near full power. As the engine is throttled back, compressor RPM falls, pressure ratio drops, and turbine inlet temperature drops, all of which reduce thermodynamic efficiency. So, when throttling back, turbojet thrust falls disproportionately to fuel flow, unlike piston engines for which specific fuel consumption stays constant or even improves at lower power settings. But the main reason a small turbojet consumes almost 4 times more fuel than a roughly comparable piston engine is only partially due to being a turbojet, but mostly due to being a small turbojet. Gas turbine engines don't scale down well and lose considerable propulsive and thermal efficiency when made smaller, compared to piston engines made smaller. This is primarily due to compressor and turbine blade tip clearances. On a large turbojet, or turbofan engines for that matter, the gap between the blade tips and the surrounding shroud is kept very tight. It has to be because efficiency is lost whenever air passes uncompressed past the compressor blades or past the turbine blades without doing work. The larger the clearances, the more efficiency is lost. Gas turbines therefore maintain a very low tip clearance to blade height ratio. But as we make smaller gas turbines, that clearance does not shrink proportionally. Halving the length of a turbine blade to build a smaller engine does not mean the tip clearance can be halved as well due to manufacturing tolerances. That means the smaller the engine, the larger the tip clearance relative to blade height. Relatively speaking, too much air is lost through the gaps and engine efficiency suffers accordingly. So it's no wonder small gas turbine engines haven't taken over for very light aircraft, let alone small turbojets. If you enjoy the content on this channel, please consider supporting me on Patreon, where members get additional perks. Membership starts at $1 per month, links in the description. Now let's look at the applications of these tiny turbojets. So what do these tiny turbojets power? Well, tiny jets, of course. The TRS-18 from Microturbo was the power plant of choice for the Microjet 200, a French light jet trainer which first flew in 1980. It's not as tiny as you might expect at 6.7 meters long with an 8 meter wingspan. Empty weight was 780 kilograms, again using the Cirrus SF50 as reference, which has an empty weight of about 1,600 kilograms. With a max all-up weight of 1,300 kilograms, it makes sense that it needed 2 TRS-18s, which together gave it a 1,700 feet per minute rate of climb. Cruise speed was 209 knots, with a maximum speed of 249 knots and a ceiling of 30,000 feet. Only a handful of Microjet 200s were built. Keeping with the TRS-18, it also powered a few other jets built in small numbers, the most interesting being NASA's AD-1 oblique wing research aircraft. While these are small jets, they aren't personal jets that a private pilot could realistically own. So let's look at some that are. The TJ100 from PBS has powered mainly 2 types of experimental jet, the BD-BD5J Micro and the Subsonics JSX-2. The latter is a home-built single-seat jet from Sonex aircraft. At least 17 have been built, so it's not a one-off type. It's also fairly modern, having been introduced in 2015. It's 5 meters long with a 5.5 meter wingspan. Empty weight is around 230 kilograms and with a max all-up weight of 454 kilograms. It cruises at around 210 knots with a never exceed speed of 249 knots. Rate of climb is a respectable 1,600 feet per minute and fuel consumption is claimed to be 68 liters per hour in the cruise. The other TJ100 powered personal jet is also a home-built, the BD5J Micro. If it looks a little familiar, that might reveal your age, as the BD-5J appeared in the 1983 film Octopussy, being flown by Roger Moore's James Bond in the opening scenes of the film. Note that the performance figures I'll use here are for the TRS-18 powered version, as I couldn't find a complete set of figures for the TJ100 powered variant. It's only 3.8 meters long with a 5.2 meter wingspan. Empty weight is just 195 kilograms and max takeoff weight is 408 kilograms. Maximum level speed is 288 knots or 330 miles per hour at sea level. Rate of climb is an impressive 2,400 feet per minute and service ceiling is an equally impressive 30,000 feet. Though flying that high is not practical without pressurization or at minimum supplemental oxygen. There are other regulatory requirements too, including the need for both the aircraft to be IFR equipped and the pilot to be IFR rated. So the BD-5J is the fastest of the lot, and with the lighter and slightly more powerful TJ100, it should be even better. Unfortunately, the BD-5 comes with both some controversy and a sobering safety record with at least 25 fatal accidents. That's over 12% of all completed BD-5s that flew. Most accidents were not engine related, but stemmed from the high level of piloting skill the BD-5 requires, compounded by the fact that it's a single-seater, meaning your first flight in a BD-5 is without an instructor. Prior to these, numerous engine failures plagued development, but those were due to the poor reliability of the piston engine variants, a problem the turbojet variants largely solved. Of course, no video about tiny jets is complete without mentioning the Colomban Cri-Cri. It's a home-built aircraft designed in France whose piston variant first flew in 1973. The jet-powered variant is officially designated the MC-15 Cri-Cri jet. The piston variant is powered by two 15, that is 1.5 horsepower single-cylinder engines. If that sounds crazy, the prototype flew with two 9 horsepower engines. The jet variant is powered by two PBS TJ20s, which are no longer listed on the website, which I assume is because it's no longer in production. Each TJ20A is 316 mm long, weighs about 2.1 kilograms, produces a maximum of 210 newtons of thrust, and can operate up to around 20,000 feet. The TJ20 sprints up to a maximum of 120,000 RPM. The Cri-Cri jet is only 3.9 meters long with a 5.3 meter wingspan. Empty weight is just 83 kilograms with a max all-up weight of 205 kilograms. At full throttle, it burns up to 78 liters per hour. Rate of climb is 1,180 feet per minute and maximum level speed is 119 knots, with a never exceed speed of 140 knots. It's definitely one of the slower aircraft in this video, but not everything is about speed, as we're about to see. Tiny turbojets don't only power experimental jets, but also some sailplanes. That may sound strange, but it makes more practical sense than might be apparent at first. Some motor gliders carry a small engine, offering the option of power if the thermals aren't cooperating. Many can't use it for takeoff but only as a flight sustainer, and the aircraft still typically needs to be towed aloft. The biggest issue with using a small piston engine in a powered sailplane is stowing the propeller blades. Some sailplanes do this successfully, but there is always some sort of compromise in the propeller design to allow it to fold away. That challenge is apparent when you consider that single-blade propellers are actually a thing in powered sailplanes precisely because they ease stowing. I've already talked about single-blade propellers in a dedicated video linked in the description. A turbojet has no propeller blades at all and are very small, which makes the stowing problem largely disappear and greatly simplifies the installation design. Of course, there's the issue of high fuel consumption, but sailplanes aren't using the engine continuously throughout a flight, only occasionally, and on some flights not at all. That makes the turbojet's thirst much less of a problem. Having seen one of these fly an airshow routine, they do seem extremely capable and fun, though obviously not their primary purpose.
Beautiful aircraft, beautiful display, flown here by a man that's got the title of World Champion many times.
One example is the JS series of sailplanes from South African manufacturer Jonker, which uses the MD TJ42 turbojet, an engine designed specifically as a sailplane sustainer. It produces 350 newtons of thrust. Dry weight is only 3.65 kg or 8 pounds, and at just 406 mm long with 148 mm cross section, it's easy to see why it suits sailplanes so well. Fuel consumption is claimed to be around 69 liters per hour at maximum thrust, but running on power for extended periods is not something that happens often in this kind of flying. This isn't an exhaustive list. There are a few more sailplanes making use of turbojets. As I wanted to focus on manned applications, I didn't cover drones, and missiles aren't really my thing. I hope this look at a more fringe engine type was informative. Share your thoughts in the comments. Thanks for watching, and I'll see you in the next one.